Welcome, folks. I am Chris Schott. I'm the host of Engadget's Explainer Show, upscaled on YouTube. And kind of my secret is I pretty much started this show as an excuse to get to talk to really smart people about the work they were doing and to try my best to understand it. And in that spirit today, I am joined here by Intel's Dr. Rich Uhlig, who is the director of Intel Labs, which is a division in Intel which is doing some really crazy, impressive work. Now, Rich, maybe you can actually just give us a little introduction about what Intel Labs' mission is. I'm not sure it's a part of the company that people are familiar with. I know everyone knows Intel for your processor designs and all the work in computing, but what does Intel Labs itself specifically focus on?
Yeah, happy to talk about that, Chris, and thanks for having me on. I'm delighted to be part of this event. So, Intel Labs
Sure.
is the research organization for Intel, and our primary purpose essentially is to explore the future for Intel. And we use a number of different methods for doing that. We engage with academic researchers. We do our own original research within the company. And we work closely with our business unit partners and product team partners inside the company to take our research innovations and translate them into a form that Intel can ultimately bring to market at scale. So that's essentially what we do.
So I want to dig into the specifics of some of your research in a second here, but how do you decide what avenues of research are worth exploring?
Well, we use a number of different criteria, and it's not so much about the time scale, whether it's far out in time or near in, but rather we look for pain points, areas where there's something that makes computing difficult for people to engage with, or sometimes we'll look for some emerging barrier that's coming. It might have to do with power or some limiter to being able to do something new with computing, and sometimes we look for enablers that will technologies that make entirely new things possible. And so, just to give some examples, several years ago within the labs, we observed that one of the pain points with working with PCs was this abundance of different kinds of connector types, that the sides of PCs were littered with. And our concept was that we should try to converge all of them onto a single I/O protocol, and that's what ultimately became Thunderbolt and USB Type C. So that would be an example of an innovation that started in the labs. But we've done similar things, like when we recognized that there was a lot of computing capability available in our server systems, and oftentimes it wasn't fully utilized. We invented virtualization technology and brought that to market, and that's been widely adopted in the cloud by cloud service providers. And that would be another example of a technology that came out of the labs. And maybe one that we could talk a little bit more about today is our work in silicon photonics, which is all about identifying a limiter, a limit to how much we can deliver I/O to compute devices. And silicon photonics is all about overcoming that limit.
Yeah, so I know this is one of your particular areas of interest, I know. So this is probably not a field that folks are particularly familiar with. You just want to give us kind of the general overview about what this technology is. You said it's trying to get through bottlenecks in I/O. So we're talking about like feeding data into the chip faster.
Yeah, that's exactly right, Chris. So if you think about, what we need from like a high performance compute device, whether it be a high end server CPU, or it might be a GPU, or maybe an FPGA, that you have to feed it data. And as it gets more and more capable in terms of the amount of compute that it can do, the amount of data to feed the beast just increases over time. And one of the things that we've identified as a impending barrier to making further progress is that just the amount of power budget that goes to I/O, just getting the data onto the chip, is taking an increasingly larger proportion of the available budget that you have, and that means that you're increasingly we're not leaving power for the compute itself, and a lot of that has to do with the limits of electrical signaling. The amount of data that you can push over electrical links is getting increasingly limited, and it's getting harder and harder to do, especially at larger distances. And so we think that there's a very exciting opportunity around moving from electrical signaling to optical communication. And we've been developing in the labs a lot of different technologies that allow you to go end to end with optical interconnect straight into a CPU or a GPU package.
So when we're talking about the current kind of electrical interconnects, that's the systems like PCI Express or things like that people are now using to hook memory and graphics into the processor.
Yeah, that's right. I mean, the predominant form of communication in computing systems today is electrical signaling. It's the more cost effective. It's brought us a long way over many decades of improvement. But what we're starting to see is that the ability to deliver high bandwidth electrical links is getting limited, especially at distance. And so what you've already begun to see in data centers is that the different servers between racks are getting connected through optical links. And what we think is going to happen over time is that those optical links are going to get closer and closer to the individual compute nodes and the different compute packages as well. And so in the labs, we've been developing technologies that allow us to integrate those optical links straight into the compute package.
So we're talking about right now in data centers, you've got the racks maybe hooked together with fiber optic cable, and you're talking about actually building an optical link maybe directly into the server, inside of an individual server itself for improving moving data between the different parts.
You got it. That's exactly the vision. And to make that possible, we've had to invent a number of different new components so that deeper integration into the compute package is possible. There's when you think about what you have to do end to end for optical links, you have to have first of all a source of light, and so we've actually going back many years in the labs have developed technologies around what's called a hybrid silicon laser, where we can generate light through silicon devices. Once you can do that, you have to be able to modulate data signals onto those optical signals over different wavelengths of light. You need ways of guiding that light from endpoint to endpoint. You need ways of amplifying that light. You need ways of detecting the light at the other end. And so there's a number of different components and physics behind implementing each of those that we've been investigating in the labs. And
So in the current fiber optics I've seen, like the ports for connecting in, I've not spent a lot of time in servers, but I've at least seen fiber optics links used in PCs and the like. And I mean, we're talking about like a fairly chunky plug that usually goes in the back of a port, and then kind of a hefty cable that strings to the next port. What level of miniaturization? Oh, we have lost Rich here for a sec. We're going to attempt to get him back online.
I'm back. Can you hear me?
I can hear you.
All right. I guess we just lost the link there momentarily. I'm not sure where you lost me, but I can. Think we're in the
We're
middle of
just
talking about
building this all kind of into the different parts you needed to build this into an actual board. I was just wondering, so what how different is this from the? I mean, I've seen the sort of fiber optic connectors used in servers, and a lot of them are pretty chunky port. I mean, maybe the size almost of like a Sharpie marker. So what scale of miniaturization are we talking about to bring this down to the level you're talking about with doing this like on a compute package?
Yeah, you're right that today's optical transceivers they are still discrete devices. They're larger in dimension and part of the reason why that's the case is that until recently we haven't figured out how to modulate electrical signals onto the optical link with devices of small dimension. And when I say small dimension, something that's small enough that you could situate it right next to the compute package. And we've developed what are called micro ring modulators that you can have as many as 100 of them arrayed around the compute package, and therefore you have the option of integrating it straight into the compute package. And what that means then physically is that you take the electrical link that would otherwise be required at each endpoint of a optical fiber, which is really sort of the last inch or so that you need to remove in order to achieve this vision of really energy efficient, high bandwidth communication at distance.
So we're talking about actually integrating tiny optical fibers onto the chips or boards themselves to form these connections.
That's right. Yep, you got it.
So one thing when I was researching this, one thing I thought was really interesting is just the idea of how the modulation works with these ring structures. For folks who maybe are not following all of this modulation, we're talking about kind of turning the signal, the light beam, into a pattern that actually carries data. And it doesn't work in the way that I thought it would. I think in my mind I assumed you'd just be sort of like turning a flashlight on and off, essentially, to get this light signal with your ones and zeros. But it's a little more complicated than that. It turns out. Do you want to talk through how this
Yeah,
works with these ring structures?
sure. There's a few different components that are coming together. To start, you've got the electronics within the compute device that are ready to send data across the package pins. And you're still in the electrical domain at that point. And you've got ones and zeros that are the data that you want to send off of the chip. Now, you also have a light source, this hybrid integrated laser that's ready to generate light at different wavelengths and send onto an optical fiber. And what you need to do is cross that boundary between the electrical domain to the optical domain, and that's achieved by what are called micro ring modulators that are tuned to certain resonant frequencies so that they can generate light at specific wavelengths that are sent onto the optical fiber, and they're coupled to the data signals that are generated on the sending side of the link. And what's really amazing about optical technology is that you can have multiple different wavelengths that all share the same optical fiber, which means that you can get much higher density of communication through a single link, something that would otherwise, with electrical signaling, require a whole bunch of package pins and wires coming off of the chip.
You're talking about, I mean, I realize the frequencies are maybe not quite the same, but essentially like shining a bunch of different colored lights down a fiber simultaneously, and they can be picked apart, and each one can carry its own signal.
That's right. They're multiplexed onto the same fiber on the sending side, and then they're teased apart on the receiving side so that you reconstruct the signal. What and so you get a very efficient use of that fiber. And also, a really important part of optical is that you can do so at distance. You can begin to separate the receiver and the transmitter by large distances, and that is also a distinguishing factor of optical communication compared to electrical links.
Yeah, what is the is there an example of what the difference is there over distance? I know, I mean, a lot of USB cables and the like that we work with in the non-server consumer world tend to max out at not terribly long. But what's possible with optical fiber here?
Yeah, so once you account for the fact that you can get greater distance with optical, and that's an important property. What happens with electrical links is that as you get you can still push higher bandwidths, but you need to go to shorter and shorter distances, and that's one of the limiters. But after that, there's different ways of thinking about performance. One is the efficiency of the link. So how much energy is required to transmit the bits of information. And so if you look at sort of best in class Ethernet style communication where you're communicating at distances, you might be in the tens of what are measured in picojoules per bit. Something like 28, 30 picojoules per bit for a long distance communication. We
So
think
that's like
that with the right
data. Just to
oh,
clarify, sorry,
sorry.
the picojoules per bit. That's essentially electricity per data moved. Is that
It's
that's what we're looking
it's
at?
amount of Yeah, it's the amount of energy. Those are the joules are a measurement of energy to transmit a bit of information, and so you want that number to be as small as possible. The smaller it can be, the more data you're able to push over the link. And so currently, with optical communications, you do have to spend a fair amount of energy to get the bits pushed across the optical link. But through some of the innovations that I was describing earlier, we believe that we can improve that by an order of magnitude or more. And so that's one way of thinking about performance, is how much energy is required to send the bits. Another way of thinking about it is what you could call bandwidth density. So this is how much space do you need in order to push data off of the chip. And one of the problems that we have with electrical links today is that we have to add more and more pins to the package in order to reach higher data rates. But because of the property that I described about optical before, where we can multiplex multiple different colors or wavelengths of light onto the same optical link, we can get much higher bandwidth density. And there we think we can get 20, 40x kinds of improvements. And you can get we want to get north of a terabit per second of bandwidth within a millimeter of shoreline around the chip package.
So we're
Now, one
talking
of
we're talking a terabit of data moved per second in and out of a chip.
out of a chip over a millimeter worth of shoreline on the chip. So we think we can even push that higher by aggregating more and more links, optical links onto the package. But you can see that you have, much more headroom for improvement with this optical technology than you would have with electrical. And that's what has us so excited about it. And we think it will really change the way that computing systems are built, because you can begin to disaggregate the different things that we think of as servers in new ways. You can separate compute from storage and memory, and you can begin to assemble systems in entirely new ways that will lead to all kinds of improvements in performance and efficiency.
So what are the odds this filters down to my SSD some point 15 years in the future, or is this mostly a high performance computing innovation we're looking at?
Well, it's probably a high performance computing innovation in the near term. But a lot of that has to do with the fact that we still have to get the cost down. And high performance applications can tolerate higher costs. However, I mentioned earlier Thunderbolt technology. In our original vision of that was going to be an optical link. In order to, even in client applications. And so ultimately we went with electrical signaling for Thunderbolt. But there's you can imagine a future where even in client applications where you're, multiplexing multiple I/O protocols at between a PC and then the peripherals that you want to connect to, if you have need for higher bandwidth, then you could imagine moving to optical links in the future, and there could be client applications as well. So it's something that would be enabled once we can bring the costs down.
That's pretty cool. I look forward to being able to connect in my external hard drives via a terabit a second link. I wanted to jump to one of the other areas that you folks have been working on at labs. One that I don't know if it's a super common area of knowledge with our general audience, but neuromorphic computing, which has a heck of a name here. Can you give us a little introduction about what this project is, what neuromorphic computing is, and what you're hoping it can do?
Yeah, sure. Let me just start by defining the term. So, the name is just suggestive of the idea that if you look at biological brains, they are an amazing thing, what they're able to do. If you think about neurobiology, we believe that there's much that you can learn from that. And so we're considering how we can take lessons from biology, from biological brains, and build computing devices that take the form, or at least mimic some of the dynamics of this kind of intelligence. And really, it's inspired by or recognizing that there's been tremendous progress in AI. We've all seen that in the last several years, and it's based on a model of artificial neural networks that really abstract away the some of the more subtle nuances and behaviors of biological neurosystems. What we want to do with the neuromorphic computing is capture some of those dynamics. In particular, the what we see in biological brains, where you have many neurons that are interconnected in a dense network, and any given neuron may fire based on the inputs that it receives over its synapses, and the each neuron is then connected to other neurons, and they can send what are called spiking messages to those other neurons in the network, and then excite one another. And so this dense interconnection of neurons is what happens in biological brains, and we're trying to model some of those dynamics so that we can see if we can build a system that exhibits some of those same qualities. And just to underscore the point, by way of analogy, if you look at something like a cockatiel. It has a tiny little brain, but it's able to do amazing things, navigate very complex physical environments. Cockatiels can even learn words and sort of parrot them out. They can even turn objects into tools. So there's a lot that can be done in a very small brain of an animal. And we're way far away from that when you think about the compute that goes into, say, a drone, where it's going to be many orders of magnitude more power that's consumed. The capabilities of being able to navigate an environment are much more limited. And so we know that it's possible. There's an existence proof with biological brains. And so what we're trying to do with neuromorphic computing is capture the essence of that and see if we can't solve some of those problems and build more efficient, intelligent systems.
So, what are these neuromorphic chips or neuromorphic processors? What are they suited for? I guess what's the advantage that they're able to provide? I know it's still relatively early days, but what can they do? I guess.
Yeah, no, great question. So, we're looking at them for a few different classes of applications. The first is the things that I just talked about. We think that they have some promise in building the control systems for robots or drones. If we think about biological brains, that's what they're really good for. If you're an animal out in the wild, being able to navigate a complex, dynamically changing environment is something that you can do with high efficiency. And so there's an analogy there in building robotic systems where we could potentially use it for a control system for, say, a drone or for a robot, and to do things that biological systems do. Things like building systems that can learn how to smell. Taking like the inputs from a chemical sensor and then recognizing what the scent is in the same way that that we can discern what's in an environment when we take in those inputs through our noses. We're using it to build systems that can touch, make sense of tactile sensors that may be built into a robotic arm. So there's a whole class of applications that are in that space. But what's interesting about neuromorphic is that it's also very energy efficient, and we think therefore that it can also be used for other classes of problems. And when we build our neuromorphic computing systems, we're not only building small single node implementations, but we're also building larger clusters of neuromorphic systems where we scale up to a really large number of simulated neurons. And we think that there are problems in the space of constraint satisfaction, for example. Like if you think of Sudoku, that's solving a Sudoku puzzle is a constraint satisfaction problem. But there's many other optimization problems that are like that. And neuromorphic systems seem to be really good at that kind of an application. Another application would be solving problems in similarity search. So imagine you've got like a really large visual database of images, and you want to find and you've got a source image that you would like to submit into that database, and you'd like to find all the other images that look like it. Like let's say you've got a picture of a couch and you want to find all the other pictures in your visual database that look like a couch. That's called similarity search, and that's something that neuromorphic systems are pretty good at. And if you think about it, there's an analogy there too, that once we with biological brains build a sort of a memory of different kinds of visual imagery, and so when we match against a new sensory input that we get, we're able to make that linkage between a past experience and a new experience. So those are the kinds of things that we're exploring with our neuromorphic prototypes.
So is it fair to say that like a lot of the neural network and deep learning algorithms that have been used in AI work for the past while are kind of doing the software simulation level of how a brain structure might work, and this is trying to actually build some of that into the actual processor design itself?
Yeah, at a high level, I think it's a fair characterization. If you look at artificial neural networks, or what are known as DNNs, they are abstracting away some of the dynamics that we see in biological brains, and that those temporal dynamics, what we see with spiking messages in a neural network, what's called an SNN, a spiking neural network, is the additional thing, or the differentiating thing. And we think that by capturing these additional dynamics, we'll be able to get new forms of efficiency. And we're also hoping that we'll be able to build systems that can learn on the fly. Because if you look at a lot of DNN designs, deep neural networks, they tend to operate in two modes. There's a mode where you train against like a labeled data set, and you learn how to train the weights of the neural network, and then you deploy it, and then you can use it for recognition and classification tasks. But it's really a sort of a bimodal sort of mode of operation. With neuromorphic systems, we want to both get efficiency and be able to learn on the fly. And that's one of the things that we're exploring with this research.
So do these chips have to be designed kind of in concert with the learning algorithms that are actually going to run on them? I know, I mean, there are like a normal processor may not be terribly efficient, but there are a lot of different AI models you could run on one. Are these kind of built in concert with the software that emulates these neural networks, or how does that designing work there?
Great question. In the same way that we design classical computers so that they can be programmed, we're doing the same thing with our neuromorphic designs. So we have a single design, and you can sort of think of it as an efficient implementation of the dynamics that we see in biological brains. But it actually doesn't look like a biological brain. It really is a bunch of cores with an on-die fabric that is able to connect those, what we call neuromorphic cores. And those neuromorphic cores are simulating what a neuron would do. And any given neuromorphic core can model a bunch of virtual neurons that can receive inputs and generate outputs, these spiking messages that I described earlier. And what we do to program this is we have a software stack, a layer that runs on top of the architecture that allows a programmer to express what they would like any given virtual neuron to do. So we have these things that we call firing rules, and it's just an expression of what are the conditions under which a virtual neuron will generate a message into the network. And that's how you program a neuromorphic system. And so through that flexibility of defining those firing rules, you can solve lots of different kinds of applications. And that's really how we're beginning to do these explorations. And I should say a little bit about how our methodology and how we do this. So at Intel Labs, we believe really strongly in collaborating outside of the company. And one of the things that we've done is set up a network of neuromorphic computing researchers outside of the company. And by the way, this is a field that's been ongoing for many years now. But what we're doing is enabling it with these prototypes of neuromorphic chips. We have a system that we call Loihi, which is a neuromorphic implementation that we've put in the hands of these external researchers. And we've also enabled them with software that allows them to express their algorithms, applications that they think may be of interest and useful to explore. And that's how we're beginning to learn what kinds of problems this style of computing will be good at.
That makes a lot of sense. And the chips you're making, the Loihi, is this built? I mean, kind of, it's the secret's just in how it's organized. Is this built like one of your other, just like an Intel processor, or does this take some special fabrication technology to actually assemble?
It doesn't require a special process. In fact, it's the Loihi design was just implemented on our 14 nanometer process. It uses regular digital logic. It's not exotic in that sense. There are some kinds of neuromorphic designs that are based on analog computing principles, but it's still a digital design. One thing that's unique about it is that it's using a different kind of design methodology, what's called asynchronous design, which is a way to get some additional efficiency without depending on a synchronous clock for that drives the advancement of the computation. But aside from that, the sort of the innovation in the design has to do with how we've built a system that's able to model the dynamics of a neuromorphic system and how you program it in the manner that I described earlier, and that's where we think the efficiency is going to be coming from.
That's very cool. So yeah, retool. It's still transistors and memory and everything, but it's the secret sauce is the organization, how it's all structured. That's very cool.
That's right. Yeah, exactly.
Where I'm taking too long. These are far too interesting topics, so I want to actually move on to another one of the things that
Okay.
that I've seen you folks are working on. This one is I have done the bare minimum of coding in my life, but I'm not a programmer. This one felt like it was at kind of the absolute leading edge of my ability to understand. But machine programming. Can you give us a little intro about what this topic is? This one was a little confusing for me. I got to be honest.
Okay, sure. Let me just motivate the problem. So, at Intel, we're primarily a hardware vendor. Obviously, we build our business on building all kinds of compute devices and communication devices, and we're very dependent on a really rich and capable ecosystem of software developers. We do our own software development too, but we really need lots of people able to program computing systems. And what we've observed is that it's getting increasingly difficult to program computing systems, especially as they get more and more complex. And we have this idea of a notion of a ninja programmer. This is someone that's like really good at getting the ultimate performance out of a computing system. And the problem is that there aren't many ninja programmers to go around for the kinds of the magnitude of problems that we'd like to solve. And in fact, while we're getting more and more programmers, those programmers are emphasizing approaches to programming that increase productivity. So they're using languages like Python in order to quickly develop code, but it's not necessarily the highest performing code that gets the most out of the underlying hardware. And so we considered that to be a problem at Intel, and we wanted to bring some technologies to bear. And the basic idea of machine programming is to teach computers how to program themselves. That's literally what the idea is. And you can take this apart in different ways. I mean, the grand vision is we'd like anybody, whether they're a programmer or not, to be able to express their intent and have a computing system do that. That's like at the highest level what we would like to achieve. And then you stop thinking about being a programmer or a coder. You just you express your intent and you get what you want out of the system. Now, that's kind of abstract and high level. And so in the labs, we really like to get concrete and make forward progress. And so a near-term vision is that we're trying to develop technologies that just make programming more efficient. As an example, a lot of time today goes not just in writing code, but in debugging it, making sure that it's correct, finding the errors in the code. And so we've been developing some new systems that are able to find errors in code automatically, and they do so by scanning lots of examples of code, and then using an understanding of what good examples of correct code look like in order to find errors in code as it's getting written, and to do so automatically. And we hope that this will sort of dramatically lower the amount of time that's spent in debugging software.
So if one of the issues is that a lot of software, even written by good developers, has bugs in it, how do you pick what you're training the system on? Is someone having to go through and write stuff that you can verify and debug and know to be valid, or how? I guess it does seem like such a widespread problem. I understand the scale of the issue, but because of that, it feels like finding appropriate training data to feed into the system would be very challenging. So how do you approach that part of the problem here?
Yeah, right. I mean, you're asking a really great question. How can you be sure that you aren't feeding the system, code that's buggy? And then if you're doing that, then how can you trust what you're getting out of it? And the short answer to that is you can't be sure that you aren't feeding the system buggy data. But you can. That doesn't have to stop you in making progress. And so, basically, what we're using is a method that's known as anomaly detection. And we sort of break the process into two steps. The first is that we point the system at a lot of examples of code, like billions of lines of production code that's out there. It's actual operating software, and so it's got to be working correctly at some level, although it may have bugs in it, right? But what we do is we just sort of uh, mine all of that existing production code for patterns, and there are distinct patterns that you can find in properly functioning code. And you can use machine learning methods for that. You can also use other forms of analysis, formal methods for understanding the structure of code, and does it look like it's a good example, a pattern of correct code. And most correctly functioning code will fall into certain distinguishable patterns, and that's what you would expect. Anomaly detection is about finding those outliers, the like snippets of code that don't seem to follow a common pattern. And it's sort of like a probabilistic approach to finding where bugs might lie. And that's sort of the second part of the process, which is scanning. So scanning all of the code the new code that you're trying to debug, and trying to identify the places where it deviates. It has anomalous structure compared to lots of examples of production code. And that, while it still requires a human in the loop to go and look at violations, pattern violations, to confirm that there is in fact a bug, you can take a lot of the work out of it by doing this automatically. And that's the basic idea that we have. We have a system we call Control Flag that we've been recently publishing some papers on, and it's actually been able to successfully find bugs in code that had been latent for many years, and were only discovered by the system.
That's very cool. It's almost enough to make me want to try to learn some more Python, I've got to say. So maybe not in the near term. Well, I know we'd put quantum computing in the title of this, but I think we're actually reaching the end of our time here, so we might have to save that for another chat in the future. Though I know Intel's doing a lot of work there as well. But thank you so much for taking the time here this morning to talk to us. This stuff is all super interesting. I know we could have spent probably an hour on any one of these topics, but it's great to get an overview of all the work that Intel Labs is doing. So yeah, thank you so much for joining.
Yeah, and happy to come back at any time.
I appreciate it. Yeah, we may give you a call for some future upscales for some some research into some of these. This has been great. Thank you, folks, for watching. Stick around. We've got a short break, and then we are back. Our editor, Sherilyn Lowe, will be sitting down with Microsoft for our next interview here, so stay tuned for that.